is not fun, is it? Hand collating. I'll start this. You're doing a much nicer collation job than I'm doing. I guess we could have just had everybody take one.
Here,
I'll definitely serve. Mr. Caden's first. Thank you. I'll take care of the rest. Thank you, Fred. I really appreciate it. We have so much that I want to get done today that I made these. You're welcome. And this is fun. I think you're going to really dig this last unit. This looks like really boring and intense, but Selena, could you please send me one more email? Just say hi. That's all it has to say. Title hi. That just reminds. What's that?
I sent one last.
Send me another one so that I see it at the top of my queue, because I knew you did, and then if I don't see that there, I lose track of things. All right. Cool. I want to get one more set of things out to you. So there is a web workup that is excellent review and will quite possibly count as extra credit if you do all of it. So I highly recommend doing all of it. Let's see here. So this is some more stuff. This is a double-sider, I believe, isn't it? Yeah. Yeah, right? Like pictures and stuff. Very fun. Lots of fun.
That's the graph theory one.
It is. Graph theory is freaking awesome.
Is it though?
Yes,
Is
it
it?
is though. Yeah, it is, Yvonne.
Okay.
Mr. Abraham had. I'm not sure. Yeah, you're not his keeper.
Not even my brother.
Oh wait, no, you're good. You're good. Yeah, yeah. Did you get a double-sider? Was that a double-sider you came out with the last one? Cool, awesome. Alrighty, my friends, we home stretch here. Probably today's the last day of, am I rolling there, Yvonne? Good, yeah, awesome. Last day of like content. Hopefully I'll get done with everything I want to talk about today. Great potential that we'll have to finish things up on Wednesday, but just at the beginning. And I would highly recommend, so no lecture on Wednesday, but I would recommend showing up because the last thing we're going to do is tricky and we're going to need practice. It's not hard, but it's an algorithm that takes like a lot of focus. And oh shit, okay. So let me get the right glasses on and let's freaking rumble. So back in the 18th century, I gotta find my little picture, there was this town called Königsberg. Where the hell is my picture of Königsberg? Ah, cool. So back when, in the 18th century, approximately 1736, there was a guy in particular called Leonard Euler, who is probably one of the greatest mathematicians ever lived. This dude touched everything and was just astounding genius in his insights. And he had heard about this problem called the Seven Bridges of Königsberg. So that's like German for Kingstown, essentially. Königsberg. There we go. Königsberg. Got the umlaut, the Königsberg. So there was a lot of rivers flowing through the city. And the city pretty much looked like this. Let's keep going. There we go. All right, so these are rivers that I'm drawing. And so those lines represent rivers. Uncrossable except by bridges. Super deep, don't want to get in, gonna get swept away, gonna break your ankles or something like that. So these are bridges. Like this. And there was this game that people would play. Like back then, people weren't like hanging out, watching Netflix and playing video games like we all do. Didn't have even phones to entertain them. So things they would do were real life things. And one of the problems was, is there a way to walk across each bridge exactly once? And it sounds like there's a clear answer from somewhere over there, just a solid no. And no one could do it. So let's just try it really quick. So is everybody with me? I feel like people are doing other stuff. Are you doing other stuff? Yeah, that's rude, don't do that. I mean, I'm up here talking. If you were talking, I would listen. So we've got these 7 bridges here. And think about what it would take to cross all 7 of them at the same time. So like say you start here. These are islands, kind of in some sense, separated by the river. So you cross here, then you'd have to, maybe come over here and cross here, and then come here. And then you have to cross one of these 2 other bridges, and as soon as you do, you're stuck. And so people kept trying to think, is there a way? Maybe there's a way to do this. Maybe I can figure it out. You see problems like this all the time on like Instagram and TikTok, right? The little ads for the games, like, can you trace this thing without lifting your pencil? I see this shit all the time. It's this problem, and this is the original version of that problem. Definitely fun to try to do it. No one knew if it was possible or not, but no one had ever done it. So Euler studied this problem and realized there's a way to take this and turn it into an abstraction. And so what he did was, he said, well, realize that this whole piece of land here is basically the same. Like once I'm in this piece of land, all these bridges are accessible to me. And then this island here is kind of, on its own. And then this island is on its own. And then this one here. So in some ways, there's really just 4 pieces of land. So we took those 4 and drew them out. And then looked at the connectivity. And as CS people, this is where graph theory comes in for you, because he realized that you could cross here and here, and so he drew that as just a couple of connections. And you can think of this as a network that we're understanding here. And then from this one, we could come in here, and we could come in here. So if you had this, let's call this A, B, C, and D. So here's C, B. So from here to here, there's 2 connections. And then from C to D, I could get there like this. And then from A to D, or from B to D. And that's really the only travel that's possible. So he turned this problem that was this physical problem into a very abstracted network problem. This is the first graph that was like officially ever drawn. So graph theory is this idea of taking connectivity and turning it into an abstracted connective diagram that expresses all the possible routes, but really only the stuff we're interested in, which is how do I travel from here to here to here to here. So this is a graph. Now let's check, we got a bunch of handouts. We're gonna have to move pretty quickly through these. So the first handout is the one that says at the top, a graph. So it says definitions, it's the handwritten. First ones we're gonna go through are my handwritten ones. We have a graph. So a graph consists of vertices. So the vertices are these nodes. Sometimes they're called nodes as well, but we're gonna call them vertices. A singular is a vertex. The things that connect the nodes or vertices are edges. So a graph is just simply a collection of vertices connected in a particular way. That's it. So that's a graph. That's what we're going to study now for, well, the rest of the semester, of which there is not a whole lot. But we're going to get a lot in here. So let's go through these basic definitions. A simple graph is a graph where no 2 edges connect the same pair of vertices. Is this a simple graph? This is not, because these two vertices are connected with multiple edges. This is a simple graph. Even though this looks like they're touching, there's only connectivity when I've got a solid dot here. So hold on, I've got to take care of Abraham. So let me see, I need a copy for myself. All right, so this simple graph, not a simple graph. We're going to work with both from time to time. Two vertices are adjacent if they're connected by an edge. So this vertex here is adjacent to every vertex except B. So check that out. A is adjacent to C, it is adjacent to D, but A is not adjacent to B. Let me get out of the way so you can see that. The degree of a vertex, this is absolutely essential, is just the number of edges coincident with that vertex. So this has degree 3, 3, what's the degree of C? What? How many edges are coming into C?
4.
5, careful. We got 1, 2, 3, 4, 5. So the degree of C is 5. What's the degree of A? 3. There you got that. What's the degree of this vertex here? 2, thank you. Playing along. What's the degree of this vertex? 1, awesome. 2, 2, 3. If I just draw a vertex, what's its degree? 0. Beautiful. Okay, so that's the degree of a vertex. Now, check it out. We got a theorem right off the bat. It's called the handshaking theorem. It says that the number of 2 times the number of edges is the sum of the degrees. So let's talk about what this says here. It says 2 times the number of edges equals the sum of all degrees, all vertex degrees. So we check that out. Here we've got a 3 plus a 2 plus a 2 plus a 2 plus a 1. And when we add that all up, what are we going to get? Geez, thank you. And so 2 times the number of edges is 10. Good Lord, I can't spell edges. But from this, I can see that the number of edges is 5, and I don't have to see the graph if I know the sums of all the degrees. So why do you think it's called the handshaking theorem? What do you think? So if we all shook hands and everyone in this room shook hands with everyone else, would there be an even number of handshakes or an odd number of handshakes? And everyone keeping track of how many people they hand shook. So how many we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We got 11 of us. So each one of us is a vertex. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Let's indicate a handshake by connecting to. Cadence and I shake hands. So I draw a connection between that. Notice that when I shake hands with Cadence, he shakes hands with me as well. So every time I draw an edge, it's adding a degree to 2 different vertices. So you can kind of, and I don't want to get into the deep proof of that, but just like kind of a rough generalization as to why twice the number of edges is the number of vertices, the sum of their degrees, because every time you add an edge, it connects 2 vertices and adds a degree to each one. Kind of simple observations, but they look pretty complicated when they're written in theorem form. Let's see here. So, look at the next theorem. Because of this handshaking theorem, if I said to you, draw me a graph, so make me a graph with 4 odd vertices. 3 odd vertices. 3 odd degree vertices. So let me be more precise. Make me a graph where you've got 1 vertex with degree 7, 1 vertex with degree 3, and then 1 vertex with degree 5. is that possible? So look at that theorem. It says, and don't worry about undirected, that just means there's no arrows on the graph. An even number of vertices of odd degree. So if this is it, this is impossible. Because every graph has an even number of vertices of odd degree. So once you add an odd degree vertex, you have to have two. They come in pairs. So odd vertices come in pairs. These are just simple facts that may or may not matter. Sometimes they're just good for intuition. Let's check out the next definition, a bipartite graph. So a bipartite graph means I can do this with it. So a graph is bipartite, just means two parts. Means I can take one collection of vertices and another collection of vertices, and all these vertices are connected to the other, but there's no interconnection between them. So this graph right here, no matter how I do this, is bipartite. This is one part and two parts, and the parts are not connected within themselves. So let me give you an example of what I mean, and show you how to do this. So one of the web work problems says, is the following graph bipartite? And that can actually be pretty tricky. So let me see, I've got one drawn in my notes here that I want to take a look at. So let's take a look at this one here. All right, so draw yourself, if you're taking notes, nice old hexagon. And let's label them all. So we've got A, B, C, D, E, F. So the question is this graph bipartite? In other words, can I separate the vertices into one group that's not connected to each other and another group that's not connected to themselves, but the two groups are connected? So here's how you find out. To tell if a graph is bipartite, this is your test. It's an algorithm, bipartite. Start coloring the vertices. Coloring the vertices with alternating colors. So I'm going to just use red and green. You can pick whatever two colors you want with two colors alternating. If this is possible, the graph is bipartite. So let me show you what I mean now with that guy right there. So I'm going to start. You can start anywhere, and I'm going to use red and green. Doesn't really matter. You can use ones and twos. You don't even have to use colors, but it's pretty. There's like a whole part of graph theory called coloring theory, where you think about coloring the vertices of graphs and all the things that can happen with that. So let's start with green. And I start alternating. And I go red, green, red, green, red, and I'm done, and it's cool, it worked out. Notice that there's no collision. So I'm going to group together all the red vertices, so I'm going to take A, C, and E, and put those together. These are the reds. And then I'm going to put the greens together down here, so those are every other, that's B, D, and F. And I'm going to connect them. And what I'm doing right now is using a thing called isomorphism. So I'm introducing this concept a little earlier than I thought, but it sounds right. Isomorphism means the two graphs have the same information about connectivity. They just look different. So with any graph, you can imagine that it's really just pins with strings between them, and you can move them all over as long as you don't break the strings or add new connections. So this one here, let's see, so A is connected to F and G. So I go A goes to, oh wait. Oh, B, thanks, sorry, yeah, that's green, not G. And then, let's see, so then C is connected to or well, I guess I'll go to B. What is B connected to? A and C. And then C is connected to D, and D is connected to E, and E is connected to F. And then F is connected to A, and I'm full circle. So notice that this graph is definitely bipartite, even though it's not that obvious at the beginning. Let's contrast that with this one here. Take 5 dots. Nice simple examples, they're all we need. So we'll call this A, B, C, D, E. And I'll start coloring. Red, green, red, green, red, collision. There's no space in there to fit a green. Does this make sense? Is this making sense what I'm saying here? So because I can't do alternating colors and color every single one of these, so let's make a little mark here that there's a collision. I would need to add another vertex, right? Like if I added another vertex and another edge, then I'd be good to go. So this one is not bipartite. Now, you've got like one problem on the web work about this. So don't like get super stressed out about how fast I'm going, because there's a lot of ideas and terms we're gonna talk about today, but if you can understand this red-green thing, you've got it. That's all I'll ever ask you to do with it. Okay, wow, was that page 1? Yeah, not bad. Page 2. Page 2. Here's where we start having some fun. So we're gonna answer the problem about the 7 bridges of Königsberg. And this is basically the result that Euler came up with. So I'm gonna put it up here on the board even though it's in front of you. Actually, first definition. An Euler circuit is a simple circuit. So a simple circuit doesn't cross itself. Simple circuit